Good morning, everyone. Welcome to part 2 of the industry session. I'm pretty excited to host this particular session because it really brings recommender systems to the space age. We have a fascinating line of speakers here who are representing companies that are working on very innovative next-generation products. And in the true spirit of Silicon Valley, this is what embodies the innovation that this geographic location thrives on. So without further ado, I will invite Manu Sharma from Shopkick. Please give the speaker a very big round of applause. Manu is going to talk about virtual shopping assistants and using recommender systems in that space. Thank you.
Thank you, Anmol. Thanks, everyone, for being here. And thank you for the opportunity to give this presentation. So I'm going to start with a question for the audience. How many in the audience here like shopping for fashion stuff? How many people enjoy shopping? How many people hate grocery shopping? Pretty good number. How many of you like deals, getting special deals and stuff? How many of you hate missing out on a good deal? Wouldn't it be awesome? Really? Just that many? Is this like a valley bubble thing? Everybody likes a deal and everybody hates missing out on a good deal. Wouldn't it be awesome if you had someone that would take out all the things that suck about shopping and make the awesome things more awesome? So as Anmol introduced me, my name is Manu Sharma and I'm VP of Data Science and Growth at Shopkick. I'm going to talk to you today about virtual personal shopping assistants. And really it's an overview of kind of how we are using data to create innovative data products and recommendations for the physical world of shopping. So I'm going to start with a little bit of an introduction about the company. So Shopkick was founded in 2009. We've raised a couple of rounds from Kleiner and Greylock. Reid Hoffman was on the board. The consumer app was actually launched in 2010, so we're about 4 years old. We have 8 million users, and we did 26 million in revenue in 2013. From the market positioning standpoint, we were named by Forbes as one of the most promising American startups, named a tech pioneer by the World Economic Forum, lots of accolades. And I don't know how many of you are aware of this, but a couple of weeks ago, the company was acquired by SK Telecom in South Korea for $200 million. Now, according to Nielsen, Shopkick is the most widely used shopping app, both in reach. If you look at the physical world shopping apps, it is the highest in reach. So after Amazon, eBay, Groupon, Starbucks, not really a retailer, it's a coffee shop. But Shopkick way up there, both in terms of reach and in terms of the amount of time spent in the app. And so there's a lot of sort of discovery happening in our app, and people are extremely engaged with the app. And so where are our users? Where do people use Shopkick? It doesn't really matter. So one of these is the population density map in the US, and the other is the Shopkick usage map. I will let you guys kind of choose which one is which, because it doesn't matter. But the one on the left is the population density. The one on the right is where the Shopkick users are using Shopkick. A key insight that we had early on is basically how mobile is changing the world. What you see here, some folks may be familiar with this. This is the election of the Pope in 2005 and 2013. Same location, in a span of 8 years, you can see the impact that mobile has had on people's lives. And really what is really interesting about this and what is unique is that it's the only computing device that you always carry with you, that is always on your person. So this provides a unique opportunity to add an interactive medium, an interactive layer in an otherwise non-interactive physical world. The consumer insight here is we talk about online shopping and e-commerce being a pretty huge market, and this is true, it's growing at a very rapid rate. But it still represents only 10% of all of retail. So in the US, retail is a $3 trillion industry, and only 300 billion of that comes from online. The rest of it is still very much happening brick and mortar. In the next 5 years, is projected to go from 10% to 15%, but still 85% of all of retail is still going to be happening in the physical world. And then we talk about the future of retail. We talk about, well, a lot of the big box retailers, a lot of big retailers are in trouble. And this is true. Retail, like everything else, has to evolve in order to stay current and in order to stay relevant, but it's not going away, not by a long shot. So the number one challenge for every retailer, any takers? What is the number one challenge for every retailer? It's always the same. Foot traffic. Get people in the door. Sell more as actually a secondary problem. In the web world, where conversion rates are anywhere from 0.5 to a couple of percent, in the retail world, conversion rates are anywhere from 20% in fashion to north of 90% in groceries. So the key is to get more people in the door, right? Once you get them in the door, they're going to convert at a pretty good rate. Next time you go out grocery shopping, especially, this is especially true for groceries. If you go grocery shopping, when you're done, take a look at the list that you had when you walked in the store and the stuff that you have in your cart. There is a huge amount of impulse buys that happen in certain verticals, right? So if the number one challenge then for retailers is foot traffic, right, then why doesn't anyone reward people for visiting stores? Why only reward people for making purchases with loyalty points? Why not reward people for just being there? Why is this the first personalized interaction that happens in the store if foot traffic is the most important thing? Why is it that the first time someone greets you by name is when you're checking out? Right? 100 years ago, when you would go to visit a store, the retailer would greet you by name. They would ask you how your family was doing, whether your children liked the cereal that you bought. So basically, to scale and by adding technology, we have completely depersonalized and dehumanized shopping. And the insight here was we need to add more technology in order to make it personal again. And so Shopkick basically our vision is to create a mobile companion that gives you a better experience at the familiar stores around you. And I'm going to talk a little bit about all the technologies and stuff that we use and how we enable this. But our vision was to create this companion. So we said, what are the things that a shopping companion needs to do for you, right? It needs to know you incredibly well. It needs to know what things you like, what things you need, what are you trying to accomplish. It needs to know your taste in fashion. It needs to know the stuff that's missing from your refrigerator or the stuff that you're about to run out. It needs to know the market really well. And we said, well, so it's not enough to know you if we don't know what's out in the market, what's trending, what's trending fashion right now, what availability is in stores, inventory, deals, pricing, right? So it needs to know the market really well. And we said we're going to support a lot of this stuff by sort of crowdsourcing or taking into account signals that we derive from the population. So this is different from shopping. This is not me and my friends shopping together. This is basically extracting signal from the community and the trends. And then it needs to accomplish certain things for you. So we came up with a key list of things. We said it needs to help you save, whether it's time. In the case of groceries, I hate going to a grocery store and loitering around for 30 minutes. It needs to save you time. It needs to save you money. It needs to help you find the stuff that you're looking for. It needs to help you discover great things you may not know that you were looking for, but when you find them, you love what you find, right? So it needs to help you discover. And how awesome would it be if it rewarded you for all of this, right? And then on top of that, value-added services and a great experience. So that's kind of what we define a shopping companion needs to accomplish for you. We work with some of the largest retailers in the country. So these are our retail partners. You go to any of these stores, you get some points for just being there. So the value prop for the retailer is that we are driving people into your stores. We also work with a lot of different brands. These are just some examples. And the way that our value proposition for the brands works is you can get points for scanning items in a store. If a brand wants to promote a certain new thing in the app, you scan that item and you get points for that. So with that, what does personalization mean for Shopkick, right? So we want to build the best real-world, hyper-location-aware, context-sensitive, real-time personalized recommender system. So there's a lot of buzzwords in here, and I'm going to walk you through sort of each one of these and what does it mean in the context of Shopkick. Some of them are intuitive and simple, some perhaps not so much. Real world, of course, we work in the physical world with the brick and mortar stores, so not an online service, but actually in the physical world. Location aware. So our service, we know when you're near a store, outside, waiting to get in. We know when you're inside the store, right? And how do we make that distinction? That's kind of how we give you rewards for walking in. So it's not based on GPS. We have an audio transmitter. So this is our Shopkick transmitter. Next time you go to a Target, try to look for this thing right inside the entrance, or a Macy's. We have them installed in over 10,000 locations in the US. And what it does is it emits an ultrasonic sound. And that sound is picked up by the microphone in your smartphone. And the sound actually has an encrypted code in it, which is specific to the store. So that's kind of how we know you are in this Macy's, in this location, and then we reward you with points. But remember, I said hyper-location aware, so what do I mean by that? What that means is we can tell when you are in a particular department in a store. So if you're looking at handbags, or men's accessories, or jackets, or shoes, we can tell when you're there. We could, in principle, this is not rolled out yet, but in principle, we could tell when you're loitering in front of a particular mannequin, and we could imagine how cool would it be that the next day you get an email saying, hey, there's a 30% off on that dress that you liked, and it's available at this store in your size. So we can do that. And how do we accomplish that? This little device is called a Shop Beacon. We've been working on it for a couple of years. We've done a nationwide rollout with Macy's. Over 4,000 of these guys are deployed, and they're deployed in specific departments. So, and they are basically using Apple's iBeacon protocol. So the app doesn't even have to be running. If you walk by the department, it can wake up the app and it can ping you and say, hey, there's a 30% off for you in the men's shoes department for the next 20 minutes, because we know that you're interested in shoes. Our holy grail is to tie the loop between online browsing. If you're a Macy's customer, you're browsing the Macy's website and you happen to see a particular pair of shoes, and then when you're in the store, make these very, very hyper-targeted recommendations that you may get it and I may not get it based on our browsing behavior. So that's what I mean by hyper-location aware. Context sensitive. So we want to be able to know when you're driving so that we don't bombard you with messages. We have a lot of since we are a location-based and real-world app, we want to be able to catch you in the moment of shopping, and that has its ups and downs. That has its downsides as well. If you're driving by a particular store, we don't want to ping you when you're on the highway. By the way, we're not there yet. We want to fix this. This is not exactly fixed right now. But we want to catch you in the right moment. So when you're driving, we don't want to disturb you. When you're at a store where we know that this is a big store and it's the only store in this location, we want to show you deals, offers, things that you have liked at that store. And when you're inside a mall, we want to show you everything that's available at that mall. We want to show you, hey, there's 5 stores where you can get kicks for just walking in. Our currency is called kicks. Sorry. So you can get kicks just for walking into these 5 stores. You can get kicks for scanning items at these stores, and here's a bunch of offers and / products that you liked here. So we want to be able to infer all of these contexts. And we do that by using geofencing today. So essentially, we have a different geofence logic for identifying big stores with a big footprint versus malls, and we use different logic of messaging when users are in these different contexts. So some examples of personalization. So what does it mean to personalize the app? Our app has a bunch of items and catalogs and deals. So an example, for example, is the feed. We want to personalize the feed. We want every user to see different pieces of content that are relevant for them. We want to personalize deals, as I mentioned. It's It's not interesting enough to say that there's a 30% deal at Macy's or Target. How much more cool would it be to say there's a 30% deal at this store, and this item that you like, you can now buy that for 30% off. So, and that is based on sort of your interests, both explicit, implicit, inferred. We want a personalized messaging, even to the extent that some people care more about certain attributes of a deal. So you might be the kind of person that really doesn't like to miss out on a deal. So if it's a one-day only deal, it may be more relevant for you. I may be the kind of person that doesn't really care about that. Unless it's a 40% off, I'm not going. And so we want to infer sort of what types of messaging and what types of things people resonate with, and personalize messaging based on that. So how does it work? So it all begins sort of with interactions in the app. We start with how people are using the app. We look at trend metrics. So we use the population sort of to identify trend metrics. What is new and trending? What is the most liked? What is the most accelerating in terms of likes and purchases and so on? We look at the deal trends. Deals have different sort of attributes to them. So what is a big discount deal ending today? That kind of stuff. We use a user's geosignature based on where you are, so that the things that are closer to you are more relevant for you. And then we look at all sorts of interactions in the app. So we use what are the things that people are doing in the app. What products do you like? What stores do you visit? Where do you scan? And then we have the ability to link your credit card, so we can say, where do you actually make purchases? So there is explicit signals, and then we use collaborative filtering to sort of infer a bunch of stuff about users where we don't have enough signals, using user or item or user item similarities. So I'll just walk you through quickly with an example of how we personalize deals. I swear this is the only equation in my presentation, so bear with me. So essentially what we have is we have a bunch of different factors that go into personalizing deals. We have the attributes of a deal, as I mentioned, ending today, 3 days only, big discount, and so on. We have the trend metrics that we get from the population. Then we have, for user-specific things, we have a retailer score. Does this person shop at this store? We have a category score. Is this particular category of products interesting to this person? And then we have a bunch of external factors about like time of year, day of the week, and so on. So essentially, we take all the attributes and trends. Then we take user-based input, which is how relevant is this retailer or brand or category or subcategory to this user. Then we take the geolocation and other external variables. All of this goes into our deals model, and then out comes a set of ranked deals for every user. And just to sort of quickly give you an idea of how we are building this, we're building this as a recommendations as a service type architecture. So this is not a complete list, but essentially on the left you're seeing what are the features that our recommendation team sort of is building as modules. And then on the right hand, on the top axis, you can see, okay, if we were to personalize deals, we would want to use 1, 2, 3, 4 things. And then our product team will pick up the appropriate set of things that they need, mix and match, and then produce a recommendation kind of from that. Very high level in terms of technology stack. We have an analytics stack. Vertica is our data warehouse. We use BigHive and experimenting with the Apache Spark. And then we have our data science track where we're using Mahout, WikaR, and Spark MLlib to produce recommendations. This is also a very high level sort of flow of data from the app going to the production tables and client logs, where we are producing all the recommendations, and then we have our sort of ad hoc stuff happening, and the query and analytics happens in our Vertica. At the end of the day, this is really not what I do. This is what my team does. So it's all about the team. And thank you for your time, and I'll take questions. Thank you.
I saw a lot of feedback from the businesses to the users to say, come in, there's a deal. What about going directly to the businesses with the user profiles? Do you guys provide like a dashboard where you go back to the businesses and sort of try to leverage your your user community for the attributes they have, their willingness to spend, and things like this? Do you do any of that sort of logic, and how valuable is that to the company?
Great question. So we actually get this all the time from the businesses. We are now in the process of creating segmentation for businesses to be able to target on Shopkick as well as off Shopkick. We're obviously very sensitive about user privacy and so on. So we want to do it in a way which doesn't compromise that. But we get it from the businesses all the time, and it's something that we're working on right now. Yeah.
Thank you for the presentation. My question is regarding the access to the data from retailers, because they have, I mean, there has been several attempts to do something similar in the past, and they've been hesitant to provide such detailed data regarding their inventory, especially the type of data that could be in detriment or in harm when you're competing with other retailers.
Right, so this is true. We currently the kind of deals and things that we have in our app are curated deals, and in terms of inventory data, this is a very difficult problem to solve. Some retailers are opening up their APIs, and I think over time this is something that will happen, that most retailers will adopt. The hardest thing, though, the holy grail, which is to actually tie the loop that a purchase in fact happened when somebody walked in. So we partner with Visa and MasterCard. When people link their credit cards in the app, we use third parties to essentially, we get a feed of net spend, and then Visa has done a study where they have done looked at people that they call twins of the Shopkick users, but they're not using Shopkick, and follow them over time, and we are able to show sustained incremental growth in revenue. So depending on the retailer, we drive anywhere from 50 to 100% incremental sales. So people that use Shopkick otherwise are identical to a bunch of other people that don't are spending 50 to 100% more at these specific retailers. But your point is right that there is a lot of sensitivity around providing data. We position ourselves as yet another channel to drive sales, not a competing threat to their existing loyalty and sort of other stuff. So they are more willing to share more things with us, but it's an incredibly hard thing to do. Yeah, it's a huge challenge.
Yeah, hi. Is the people here in the US engaging with the app? Are they using the app? And are you also planning to roll out this worldwide?
Yes, so as I showed earlier, we are the number one in terms of app engagement according to Nielsen. So on average, if you look at the engagement, people are spending about 2 hours per month in the app. Compare that with Target, which is about 15 minutes. So one of the key insights that we have here also is consumers are not going to use 40 or 50 different retailer apps just because there are 40 or 50 big retailers and you shop at a bunch of them. So we are a content app across retailers and a reward app across retailers and a deals app across retailers, and that's what people want. And so yes, the level of engagement is extremely high. The answer to question number 2 is yes, we are going to roll it out, but it's not unlike LinkedIn where you make it available. It requires a lot of business development efforts to partner with retailers and brands. We're going to be rolling out it in Germany as our first market, and then hopefully there's no end to that.
Just one last question, please.
You've described the deal recommendation process as if the deals all exist, and the only question is whether to recommend those deals to one person or another. It seems like the natural evolution of this, what the retailers would really like, is to not make all the deals available to everybody, but to only make the deals available to those people who are price sensitive, for example.
That's exactly right. So with the beacons and the department level recommendations and department level interaction that we can do now, you can make deals available, specific deals available to specific people based on whatever attribute that the store wants, and that's definitely something we're working on right now. As it stands today, the deals what we have in the app is store-wide deals, and what we want to do is it's really a similar to sort of, it's an ordering problem, given all the deals that you have, which ones are relevant for which person, so you want to show them the best ones right up front on the top. But the natural evolution is exactly what you're saying. Show the right deal to the right set of people that maximizes conversion and adds value. Yeah.
Thank you.
Thank you.
Thanks for the fascinating talk and the application. Next up, we have Eric Kondrechko, who is the Director of Science for Climate Corporation, another very innovative product and application. So with that, Eric, all yours.
Good morning. Just while getting set up, I'm going to be talking about a very different topic, and I'm wondering how many people in this room have a connection with agriculture of any kind? Okay, a couple. We'd be able to fix that buzzing. I can just plug in for that. Is that better?
That's audible and no buzz. So.
Okay. So I know what everyone is thinking. I live in Silicon Valley. I drink Soylent for sustenance. What does agriculture have to do with me? So I want to take you through a little bit of a journey. First, I think it's very important to just understand the context of agriculture today. And there's some very interesting challenges we have as a species on the planet with regard to agriculture in particular, which I want to talk about. And then I want to talk about how data science is so important. Data science is so important in meeting that challenge, and in particular, how recommendations as a specific technology can be used to improve the human condition.
In the mid-20th century, agriculture went through a green revolution that significantly increased yield. Norman Borlaug, an agronomist, led the charge to introduce high-yield, disease-resistant wheat varieties to Mexico, Pakistan, and India, saving more than 1 billion people from starvation. His legacy continues to improve yields year over year to this day. Fast forward to today. The global population is exploding. We have 7.2 billion people on the planet now, with an expectation of 9.6 billion people by 2050. Due to economic growth, especially in the developing world, the per capita consumption of agricultural products has also steadily risen. Can we keep up with growing demand? Even accounting for yield increases due to the green revolution and other technologies like biotechnology, we are falling short. With current global trends, almost 60% more food will be needed by 2050. What if we cannot increase yields to meet expected demand? When demand outweighs supply, it means the price of our food will increase. For those in the developed world, a small increase in the cost of food will not have a huge impact on quality of life. But for almost half the world's population, who live on less than $2.50 a day, it's a much more serious problem. So how can we increase agricultural yields? With all of the advances in precision agriculture, combined with the ability to learn from large data sets, we can now use data science to analyze weather and crop data to dramatically increase yields, meet demand, and make more efficient use of our resources. Predictive analysis of this data can help us reach our worldwide food security goals. Using a data-driven scientific approach, we can understand the microenvironment where the crop grows and how grower decisions, combined with the weather, impact that environment and the yield at the end of the season. Using this understanding, we can optimize decisions to increase yields.
How many people have heard of Norman Borlaug? Anyone? Okay, a few people. The curious fact about Norman Borlaug is that he almost didn't go to high school, which is a pretty surprising twist of historical fate, because it's interesting to think about what would have happened if he never did go to high school. So to set the context a little further, I want to talk about the life of an agricultural producer today, and I'm going to focus mostly on agricultural producers in the US. Someone who is growing a crop in the US today needs to make a large sequences of decisions throughout the growing season. Starting at the beginning, before even considering planting a crop, there will be decisions about equipment or land purchases, decisions related to analyzing what has happened in the past, and they may do this on their own or with the help of an expert, decisions about which crop to plant, and that will be influenced by information about the commodities market, land cost, and information about expectations about commodity prices in the future, and then also selection of seed. And then before planting, they need to make some decisions about how they're going to manage fertility. They may apply fertilizer to their field in the spring before planting, for example. And if they're irrigated, they may have to manage the state of the amount of water in the soil before planting. Then there's a mad rush to plant the crop when the weather conditions are ideal, and that creates a tremendous logistics challenge and a lot of individual day-to-day and hour-by-hour decisions need to make to do that well. And then in addition, there are very fine-tuned technical details about how the crop is put in the ground that have big impacts on how the crop performs during the season. And by the way, I should just set the stage to say that every single one of these decisions is strongly influenced by the weather that has happened in the past up until today, and the weather that is likely to happen in the next days and weeks, as well as the weather that's going to happen throughout the rest of the season. During the season, they need to know which of their fields they need to travel to, and that could be traveling by car or truck for 50 to 100 miles away to go inspect the field to see if they need to make any additional inputs to address issues of disease or pests. And then also they may need to make additional fertility decisions. And then at the very end of the season, the similar logistics challenge that applies at planting applies at harvest as well. And they also need to decide at some point how they're going to sell their crop in the market. And that could be a combination of selling it now, keeping some of it in storage, and selling it later. It's hard to underestimate some of the logistics and other challenges that are involved here. So for example, in this year, it was a very wet spring, and 150 million acres of crop was planted in about a 10-day period in the US, because that's exactly when the weather was amenable to planting. The other challenge that faces agricultural producers is that they need to make these decisions every single year, and there are about 40 decisions that are made, roughly 40 decisions that are made during the growing season, but you only get to observe one outcome. So you make a series of sequential decisions, and you can think about this formally as a sequential multi-arm bandit problem, but you don't get to see your payoff until you've done that for 5 or 6 months, and then you get to see what happens. And all of these decisions are stochastically influenced by weather events. The other interesting challenge is that you only get to do that about 40 times, because the average grower will only farm about 40 seasons. So think about yourself in a grower's shoes, and think about getting only paid 40 times once a year, and think about having a huge amount of volatility in your paycheck that's mostly weather dependent, but some of which you can control. It's because of this tremendous learning challenge that we have tremendous opportunities to provide information to make these decisions better. So I want to talk a little bit about how data science can be used to help growers make more informed decisions. And we can think about this as being an inevitable turning point in the technology used in farming. And this is an industry that has seen many transformations in the past. We talked about the green revolution. This was mostly the work of people like Norman Borlaug, breeding crops and identifying crops that would be successful in certain geographies, like India, for example. That is still continuing today, those trends, and still increasing yields, particularly in East Asia, for example. Other technologies, in particular biotechnology, which can be expressed through more efficient breeding, or can be expressed through the development of specific traits and transgenes. And a new revolution, which we call the green data revolution, which is to use all of the data collected to try to optimize each and every decision to improve worldwide yields. And so if we think about any data science problem, there's a combination of typically three things that need to be there to have a successful outcome. So one is you need to have a real need, a real business need or some other need. And I think that we've established that there's a real need to solve problems in this space. The next is you need to have data, and we'll talk about that in a moment. And the third is you need to have the expertise to solve the problems. So we'll talk about that in a little bit as well. On the data side, there is a tremendously rich collection of data from a variety of different sources that can be brought to bear on these types of problems. Just to give you an example of the size of data scales that we're talking about, if you just look at a single crop, in this case this is a corn crop in the US, which is planted on about 70 to 80 million acres typically each year. When that crop is harvested, it's harvested by very automated machinery. Typically, the only thing you need to do is press a button to turn once in a while, so you can watch the football game while harvesting. And that machinery collects about 14 billion observations every year. That's just at harvest time. If you do other things with similar machinery, you can multiply that by 5 to 10. If you use a variety of different remote sensing platforms, and these are satellite platforms that are collecting multispectral imagery of the Earth, and a lot of that imagery has direct applications to understanding what's happening in the plant. One of those satellite platforms just over the US generates about 260 billion observations in a single growing season. And then of course you have weather observations, and depending on your spatial resolution and temporal resolution weather observations, you can get another 20 to 100 billion observations. So it's not that we lack for data. That's the good news. It's not that all this data is available in a big data set that you can download, unfortunately, but it's there if you look for it. And so with respect to the problem that we are trying to solve, we can think about a theoretical learning problem where we aim to learn a mathematical function that will tell us what yield we will obtain if we have a certain genetics for a crop planted in a certain environment. An environment you should think about as being a combination of what happens in the atmosphere, the weather in particular, but also what happens on the ground and how those two things interact. And the environment is very complex and rich. It's the interaction of things like precipitation, things like soil, as well as microorganisms in the soil, as well as the topography and everything else that creates the environment that the root system and the plant is in. And then finally, the one lever that someone has control over is practices. What do you do to the crop? How do you plant it? How do you apply fertility, et cetera? This is the theoretical mathematical function that we aim to learn. And if we had such a function, we can think about increasing agricultural production around the world as a constrained optimization problem. Within every environment, we can select optimal genetics and optimal practices. And because there will always be weather volatility, we are not going to get a deterministic outcome, but we can move the yield distribution to the right and increase yields. So that's the high-level vision and goal. And I'm going to talk about some ways at which we can get to that mathematical function. There's a few challenges here, and some of these will look very familiar to people in this room. And I think about the challenges as being in two categories or two classes. So one class of challenges on the data side. One is, that's not explicitly listed here, but I mentioned before, is just collecting the data. There's a lot of data available, but that doesn't mean that it's necessarily easily accessible to someone in data science to use it for a particular application. The data tends to be spatiotemporal in nature. So in particular, the query patterns are spatiotemporal in nature. So that creates some storage challenges. The data is sparse. It tends to be, have a lot of missing data. And it tends to be very noisy. All of the data in this problem comes from some sort of measurement process, either from remote sensing systems like satellites or for local machinery, and it's all subject to some kind of measurement error, and typically there'll be a lot of variability in that measurement error. In addition, there are some tremendous learning challenges which should look very familiar, I suspect. The primary learning challenge is probably related to latent features, in that the way that the terms in that equation we had before interact is through some very complex latent mechanics. And those are difficult, typically, to uncover from the data. There's also a curse of dimensionality, which is pretty severe in this case. If you think about all of the combinations of different genetics that we know exist in plants, with a combination of all the different types of weather conditions, for example, and then combine that with all the different types of practices, and these are sequential decisions that are made throughout the season, the dimensionality of the space gets extremely large. And the final challenge is that typically you're not interested in, although I suggested we were interested mostly in yield, but typically you're not interested only in yield. You may also be interested in nutritional content, for example. So you don't aim to increase just yield, but also to increase yield and nutritional content. And you can think about that as being a multitask learning problem. So you don't need to learn just yield, but other properties as well. If we think about some of the latent feature space a little bit, and you think about this physically, it looks a little bit like this. At the surface, we have the genetics, environment, and practices. And the environment is expressed through what's happening in the soil. And inside the soil, there will be hydrologic processes, as well as fertility processes in the soil. And then all of those are influencing the plant growth and development over the course of the season. And that is, at the end of the day, what's producing the dependent variable yield. So let's think about recommendations in particular. We can think about recommending during the course of the season at each of these decision points an optimal decision to a grower. And we'll talk a little bit more about that in detail. But as a high-level approach, there are multiple ways we could solve problems like that. One approach we could take would be something like a collaborative filtering approach, where we think about it as being a sparse matrix that combines the different fields and the different genetics, practices, and weather, and then using a collaborative filtering approach. I'm going to talk about a modeling approach, and I'll talk about why a modeling approach is probably better in a minute. In the modeling approach, we can model either explicitly the physics that are going on that we talked about as being in latent feature space, or implicitly by thinking about this as a generative process, and we're observing certain points in this stochastic generative process. So we tend to take this modeling approach, and I'll talk about that in a minute. If we apply these models to this decision-making process, and we think about these decisions as being part of a sequential multi-arm bandit, at each decision point, we can present someone who needs to make that decision, in this case an agricultural producer, a recommended course of action. And that recommended course of action can be thought of as just being a conditional expectation, expected outcome maximization. There's one big challenge with taking this approach, and this is a challenge that I think a lot of people are probably familiar with, which is if you're an agricultural producer and you are making one of these decisions, you have a tremendous history related to applying judgment and expertise to making that decision. And the reason is because the amount of money that's on the line typically for a grower is about $1 million each year. So when you're making this decision, you have about $1 million on the line. And if you get an output from a model, the number one question you're going to ask when given a recommendation is, why is that the recommendation? And you may go into great depth as to why that's a recommendation. And if you take a model approach, you can surface as much information as you need to convince the grower that that's a good course of action and to explain why that's a good course of action. This doesn't just have impact on financial outcomes and yield outcomes for individual growers, but this has the potential to provide a tremendous environmental impact as well. In the Gulf of Mexico, there is a serious concern with hypoxia. Hypoxia is when the oxygen concentration in the water is below a certain threshold and the marine ecosystem collapses under those conditions. There is an ecosystem of algae, phytoplankton, and bacteria that is forced when you have nutrient loading in the water to accelerate and to deplete oxygen from the water. That nutrient loading comes from fertilizer runoff because growers are over-applying fertilizer. So this same technology and the same recommendation that you're providing a grower in aggregate can have tremendous environmental impacts. In particular, if growers are on a local optimum with respect to decisions around fertility practices, depending on the weather, they may need to move their fertility practices slightly around that local optimum, and doing so can save significant amounts of wasted nutrients, prevent them from entering the ecosystem. In other case, we may be able to move growers from a local optimum where they're at today with respect to practices to a new optimum that has significantly lower nutrient requirements, but that will require substantial effort in terms of convincing them that that will actually pay off. So I think all of the pieces are in place to be able to have a huge impact on the world through data science by applying it to agriculture. Thank you.
So this is really interesting. I am just curious, obviously you can empower farmers, individual farmers or consortiums of farmers to make more efficient decisions for themselves, but do you have any idea what the best way to incentivize to make an overall efficient solution will be? Like, I mean, who do you hope to work with in order to, you know, like as opposed to just making one farmer more rich? You know, just
yeah, so we make our tools available to all farmers, and the beautiful thing is that the incentives are all aligned. So an individual farmer does not want to overspend on fertilizer, and fertilizer is expensive. And so they're incentivized to apply just the right amount of fertilizer they need to reach whatever potential yield they can get, but no more. It's just that they may not have enough information to make that optimal decision. So we can empower them with that information. And then if everyone collectively is more efficient in their fertilizer use, then the aggregate environmental impact is great.
This is very exciting. Thanks for the talk. So you mentioned that one of the main challenges is you have the long sequence of decisions and only one output variable.
Yes.
At the end of the road, right? It seems to me that there should be some intermediate dependent variables that you could observe as well. I mean, as soon as the plants start to grow, right, you could somehow measure the growth and the shape and the appearance of the plants, right? And even, I mean, you mentioned the over-fertilization, for example. Right? Could you not, for example, get some feedback to the farmers if they over-fertilize? You could measure that there's, for example, too much runoff of fertilizers into nearby rivers, that kind of stuff. Could you not generate more dependent variables that you could observe throughout the season?
Yeah, in fact, there are a lot of dependent variables that you observe throughout the season in terms of the crop physiology. And many of those you can observe from remote sensing systems, but they tend to be a little bit one-sided and censored in that you can observe when things are suboptimal. So it's easy to observe when you have too little fertilizer, but it's harder to observe when you have too much fertilizer, especially from a satellite platform. But there are other opportunities, I think, related to what you mentioned, like measuring runoff in the river systems, and you could see if in aggregate there's too much fertilizer being applied.
One last question, please. Hi. So it's really interesting. I'm mildly familiar with combines, having written one for the first time last year, but I guess my question was more along the lines of the data set and like assuming that some of that data is coming from combines, like how do you deal with like kind of deterioration of equipment and the fact that you have a lot of turnover in, you know, reused farming equipment and like how that kind of comes in and impacts the data?
Yeah, so like I said before, all the data comes from some measurement system, and some of those measurement systems are much better than others. So some combines may be measuring well, some may not be measuring very well. We actually have, as part of the Climate Corporation, a company that makes yield measurement equipment so that we can get accurate measurements. The other dimension of that related to data, which is important to mention, is that there's a tremendous data privacy concerns. Just like in many other domains, farmers are extremely sensitive about making their data available and how it will be used. And so that's another serious consideration. And we have some very specific guiding principles that we apply to how we use data from growers, ultimately to benefit them, but exactly how we do that.
Thank you, Eric. Fascinating talk. Thanks for taking up the cause for social good. Next up, we have Eric Colson, who's the Chief Algorithms Officer at Stitch Fix, another very innovative company which is blending human computation and recommender systems to do personalized style recommendations. Thanks, Eric.
Okay, so this crowd is no stranger to recommendation engines. They've been around for a while. In fact, they may have been around for a very long while. There's many that will argue that this, powered by a knowledgeable store clerk, is the analog version of that, which is powered by machines. Now, while they may perform a similar function, I will argue that they are not alternatives for one another. They have very different capabilities. Let me illustrate. So most of the people in this room appear to be human. Maybe a few questionable ones back there. By show of hands, how many of you could find the eigenvalues in this matrix? Nobody. There's usually one or two that think they can. And the truth is you all can. It's just going to take you a long time to do it by hand. And you're going to make a lot of mistakes along the way. All right? Now, to a machine, they can do this flawlessly in just a few milliseconds. Let's contrast it with this task. How many of you could find the angry dog in that set of images? All right, we see hands. Yeah. Most of you will find it in about 300 milliseconds, and it's going to be spot on. Now, a machine is going to struggle with this. It's not going to take them a long time, but the accuracy will become suspect after many permutations of this exercise. So there should be little doubt that they have different capabilities. Machines are far better and far more efficient at processing structured data, while humans, I will argue, are far better at digesting the context, meaning, and norms that's conveyed through unstructured information. And it turns out that there are problems that call for the precisely for this combination of capabilities. I happen to work for a company that has such problems. It's called Stitch Fix. It's e-commerce, but a bit different. You can buy clothes from us, but nowhere on the website will you find a browse page, a product page, a search box. You're not even going to get recommendations here on the site. At Stitch Fix, the customer does not pick out the clothes. That's the value proposition. There's a lot of people who don't want to shop. They don't have time. They don't know what's in style. They don't know what looks good on their bodies or what's appropriate for their age. They want help with this. They want to outsource it. So here's how it works. If you were a customer of Stitch Fix, it's women only. Sorry, fellas. First thing you need to do is come here and fill out a style profile. This is where you tell us things about yourself, your height, your age, your weight, your size, your preferences for style, your preferences for fit. You can even write a free-form note that tells us pertinent things about your lifestyle that could be helpful. You can also make a Pinterest board of things you like that you can share with us. Anything that's going to help us pick out clothes for you. Next, an algorithm is going to run, one that leverages all of that data that you told us. Okay? And it's going to recommend 5 things for you. The next thing that's going to happen is we're going to ship those 5 items to your home, sight unseen. The first time you see them is when they hit your doorstep. Okay? That's when you get to open the box. You get to experience them. You try them on in the privacy of your own home with your own wardrobe, your own shoes, your own mirrors. You get the feedback from a loved one. Okay? And you only pay for what you tell us you're going to keep. You can send the rest back, repay shipping both ways. You can send it all back if you want. Okay? The shipping's on us. So that's how it works. It's a recommendation engine, but with a much greater commitment because we're physically going to ship them to you so you can experience them. And of course, behind this very different business model is data and algorithms. It's our most important asset. Now, data and algorithms are important to a lot of companies. To some, it drives incremental sales. To others, it is the means for engagement. And to others still, it is the primary vehicle for discovery. But to us, it is everything. 100% of what we sell is from our recommendation engine. And we have severe penalties when we get it wrong. To these other companies, the incremental cost of a poor recommendation is a shoulder shrug. Incremental cost. If you do it persistently for a long time, you're going to have big troubles, as the numbers show. But on the margin, the incremental cost of a poor recommendation is a shoulder shrug to them. To us, it has significant cost. We have the cost of shipping both ways. We got the cost of that inventory being out, and we have a very upset customer. To her, it is not a shoulder shrug. She may have been counting on the stuff for some event she's going to her. It has to be relevant. All right? So given this importance, the fact that 100% of our stuff is sold through recommendations and the fact that we have severe penalties when we get it wrong, we have to leverage every bit of data we have. Let's take a look. This is a customer tuple, a lot of the information that describes her. And let's take a look here. So you see up here we have a lot of structured information, size, height, age. These are things with very well-defined domains of value. And you can see how they can be relevant to making recommendations. And if we go down further, we have more structured information, past purchases, right? And you can see how this is relevant. But look at the stuff in yellow. It's unstructured. We have a free-form note from the customer's profile. She says, I'm a teacher. My clothes need to be appropriate for the office administrators as well as for third graders. Okay? We can see how that is helpful. And look down a little further. Here's where she submitted a Pinterest page, a Pinterest pinboard for us. If you were to ingest this URL, you'll get back a bunch of images of things she liked and wanted to share with us. So you can see how that would be relevant. It's all relevant. But to use it all, we're going to need diverse compute resources. We can use machines for that structured stuff. For that stuff in yellow, we're going to need humans. This is a problem that calls for precisely the combination of their capabilities. So we need both machines and humans. On the machine side, this is all the stuff that's near and dear to our hearts, right? We can do lots with structured information in machines. We can do matrix factorization to find the latent attributes that might predict what makes somebody buy things. And we can use machines to perform PCA and SVD to find the directions of attributes that matter the most. And we can use machines to get creative with our feature modeling. We can compute a number of distance or similarity measures between the customer and the product. And we can use machines to find clusters of customers or products with similar characteristics. And machines are great for mixed effects models where we can capture the interaction with every attribute of the customer and every piece of merchandise. And we can use machines to take our calculations and express them as probabilities. Right? These are all the things that work extremely well with structured data, and machines are fabulous at the computation. But we have not touched that unstructured data yet. The images, the text. We need to leverage that stuff. We can't leave it on the table. So for that, we turn to a different resource. Now, the idea behind human computation is that machines are going to perform a function, and they're going to outsource certain steps to humans. And they're going to get the results back and then finish their processing. That is, humans are not merely a user in the system, but rather they are an active participant within a greater coordinated function. Now, the system what we've built is not for lay tasks. We can't use Mechanical Turk for this. We needed expert humans. These are experts in the area of fashion merchandising. So we use them to perform 3 tasks. As I alluded to, unstructured data is extremely valuable. There's an example of a Pinterest pinboard that a customer made for us saying, hey, these are things I like. Can you take them into consideration when you do your recommendations? It's extremely relevant. And down there is a note she wrote in, would love things that I could wear to work and then to date night after. Okay, it's relevant. We can't ignore these things, but machines are going to have a difficult time with this. So we delegate the task to humans. They can do it in a snap, especially an expert human. In addition to unstructured data, there's 2 other functions that we delegate out to humans. Curation. You need to look at these 5 things that we're recommending and see them as a cohesive collection. They don't necessarily have to be outfits like this, but they need to be themed in certain ways. They can't be too similar and they can't be too dissimilar. Our machines struggle with this. We just simply don't have the co-occurrence in our historical data to compute these things. It's incredibly sparse. Our inventory turns quickly, and most things just don't co-occur. Also, machines lack the appreciation for aesthetics to make the judgment call. But our expert humans love doing this, and they can spot things in a second if they're incongruent or not. And lastly, our humans are much better at fostering a relationship with the customer. You can see here our stylist is writing a note back to the customer, and these notes include things like styling tips and some transparency for why we picked what we picked. The humans have a wonderful skill for empathy, and their prowess for articulation allows them to connect to the customer in a way that engenders trust. So these 3 things are strictly in the purview of humans. And by using these diverse compute resources, our algorithms leverage more data and more processing. Oops. They are not alternatives for one another. Their contributions are complementary and additive. Okay, yes, you say, I get it, but how does it scale? I get this question all the time. And it turns out they scale fine, as long as you couple them with technology. Our engineering team built a very slick web interface that allows our humans to work from anywhere and on a very part-time basis if they wish. And this allows us to tap into a very distributed workforce, which means we can provision all the resources we need. In concept, it looks something like this. Do we have AWS users out there? A few? All right, well, if you use AWS, you'll be familiar with this. This is the console where you go to provision your compute resources, and you have lots of options available to you depending on your needs. So in concept, you can think of us having one additional compute resource. Expert human judgment in the area of fashion styling. And we can expand or contract these just as we do the other compute resources. They're completely elastic. So we can provision these as we need them. And here's how it all comes together. So it's a busy slide. We have our compute resources here, machines and humans, and then our logistics system over here, which provides additional benefits. Now, first thing is you need some redundancy here. Both machines and humans, each resource can disappear on you without a moment's notice, so you need some redundancy there. And to scale, you need to parallelize. You need lots of each. But machines and humans have very different work styles. The machines work very quickly, and they're nearly infatigable. Our humans work a little bit more slowly, and they like to take a lot of breaks. So to coordinate their activities, we use this queuing system. So here's how it all comes together. So that's a customer out there. So once she has her style profile filled out and she wants to get a shipment of clothes, she merely needs to go and pick a date. When does she want to receive the shipment? That creates a shipment request, which goes onto a queue with a lot of others. And we route first to machines. It's important, the sequencing is important. You want to go to machines first because they are less expensive. They're more expensive human counterparts, they're costly. So what you want to do is cut down the data, order and rank it so it makes the processing much more efficient when you go to the humans. So it goes first to machines where they're going to leverage all that structured data, all that stuff we talked about earlier. And they're going to qualify and rank all the merchandise in the context of that customer. And they end up generating a list. Here's all the things that we could send her that we think she'll like. And then that list goes back into the queue. Now next it gets routed to our humans, right? We haven't looked at the unstructured data yet. We can't ignore it. So it gets routed to the humans. They open it in this very slick interface, and it overlays all the unstructured data with it so they can make sure that these recommendations are consistent with what they're telling us through the unstructured data. They perform the task of curation, and they write that note back. They foster the relationship. Ultimately, they cut it down to exactly 5 items. All right? Now it goes back onto the queue. Now at this point, we have exhausted all data. All unstructured data, all structured data. We've performed some additional processing. There is nothing left to do but to have the customer experience it. There's no point in showing her a recommendation on a web page or on an app. You can't evaluate this stuff from images and text. We've already exhausted all the data. The only thing left to do is to have her experience it. And so our logistics system handles the pick, pack, and ship, and they wrap it very beautifully and put it in a box with tissue paper because presentation matters, the experience matters, and they ship it off to her. So it's about more. It's about using more data and more processing and providing more benefits. And all that stuff adds a lot of value to her. Now, what about feedback? So, as I mentioned, the humans are not merely a user in the system, but a resource within the same system as machines. And the benefit of keeping them in the same system is feedback. So, of course, we get feedback from the customer. And that informs both machines and humans. But this feedback loop is expensive. It's going to cost you. I mentioned the cost of the shipping, the cost of the inventory being out, and the cost of alienation to the customer when we get it wrong. So it's an extremely costly information cycle. But there's a better feedback loop, a less expensive one that exists right here between the humans and the machines, our compute resources. So in the process of doing their tasks, they're leaving feedback for one another. So as the humans take that machine-generated list and they process through it, skipping things or rejecting the machine results altogether, that's leaving feedback for the machines. Likewise, the machines often expose biases on the part of the humans. In either case, we learn and we get better. And this feedback loop, is so quick and inexpensive that the system naturally gets smarter with usage. Okay, so how well does it work? We have lots of measures of accuracy. The one I'm going to show you is just the most visual. We call it predicted versus actual. So on this axis, we have our predicted probability of purchase. For each customer and everything we could send her, we compute a probability that she's going to buy it. And we do that for all customers and all products, all pieces of merchandise, the product of the two. And on this axis, we put the actual outcome. Now, in reality, the outcome is binary, right? She either buys it or she doesn't. But to make this graph work, we can aggregate things. So we can take, for example, all the pairs of customers and pieces of merchandise that we said were about 40% probable of purchase. We can take all those things. Let's say we have 100,000 of those things, and we send them out. We get to know the right answers in that case, right? So if we took 100,000 things at 40% probability of purchase, and we send them out, then if we're worth our salt, about 40% or 40,000 of them should get purchased. Okay? So this green line is the line of perfect prediction, and we'll repeat that process for every point on the horizontal axis. So how does it do? Well, I was daunted by this task. I didn't know that it would work as well as it does. And here's our results. That is beautiful. right? This is what you get when you combined machines with expert human judgment. You were able to predict with really good accuracy. You can see there are error bars on here. They're just really tight. Smaller samples out at the edges. Perhaps a little bit of bias in here due to our assumption of item independence. But this is really remarkable. And it's amazing what you can do when you get to here. There's a lot of applications that come later after this. So in summary, you can leverage more data and more processing by using diverse compute resources. You use the machines for the structured data, expert humans for unstructured data, and also the tasks of curation and fostering that relationship. Together they are better. Their contributions are complementary and additive. And together they get better and better. By sharing feedback, they enable each other to learn. So one last thought, and I'll take some questions, and that thought is this phrase, Stitch Fix for blank. This is a phrase we hear from our customers, and we begin to say it around the office too. People wish they had a Stitch Fix-like service for other things, right? So we hear things, I wish there was Stitch Fix for wine, or Stitch Fix for mountain bikes, Stitch Fix for recruiting, or Stitch Fix for fraud detection. And I actually hope that this model does spread to other industries and domains, because when you combine the power of machine learning and expert human judgment, it adds a ton of value. And I can't wait to see what emerges. Thank you.
Hi, thanks for the talk. Going back a few slides, you mentioned that computers aren't very good at looking at unstructured data.
Mm-hmm.
And I'm wondering whether it might be a case that you just don't have the right data to plug into models. So if you think of Polyvore, if you think of a lot of internet websites that have tens of thousands of outfits that have been created and a lot of feedback from customers in terms of purchases, etc., it might actually be that there's sufficient data out there to compute, to predict outfits based on that, rather than having to sort of have the human loop. And secondly, if you have that data, then you could actually, or rather you can use your humans to tag data, to tag outfits, etc., rather than getting the humans to sort of filter down the list.
So the question was really around this part, this curation part, right? Right now, there's not...
Whether you don't have the right data.
Right, so you're implying the co-occurrence of things, maybe all the different combinations of sets can happen out there and we can learn from them. The challenge is that the inventory is very dynamic. Women's clothes changes quickly. So as I mentioned, these matrices are incredibly sparse. The co-occurrence is incredibly sparse, right? And in fact, we've sent a lot of, we call them a fix, is a shipment of clothes. We've sent a lot of fixes. I can't tell you the exact number, but it's big. And never once have we sent any two customers the same 5 things, right? And this is incredible. This was amazing to me because we have no explicit attempts to prevent this. It just happens because we personalize so well, and also more relevant that we keep our inventory very large. And so when it's a N choose K problem, right? So when you think of the number of permutations of 5 things you can make out of all those different, that set of inventory is quite large. It's incredibly large, trillions, right? And so the co-occurrence just doesn't happen. It really doesn't, not when you're looking at the numbers we have. Even, you said tens of thousands, even millions and millions and potentially billions. I doubt there'll be all the combinations of 5 that can possibly happen.
Here.
Oh, there you are.
So you have shown that line with a great coincidence between predicted and actual.
Yeah.
But it is not clear to me how you get that predicted number when you have human in the loop, because computers are good in giving this probability number, but humans are not. So how do you do that?
It's a great question. Actually, it's the machine. The horizontal axis was the machine-generated probability, right? And there's an information bias, as you point out, that we actually only get to know the right answers for the stuff that is selected by the human and goes out. So we might say, these things are 75% likely to get purchased, and there's a lot of them, hundreds of thousands, but only these 50,000 actually go out, right? So the other ones, we don't get to know the right answers, and they don't make it to this chart. So you're correct, there could be some information bias on here. I have not seen any evidence to be worried about it to this point, but you never know what you don't know. So good observation.
So, Eric, I'm curious about a different kind of bias right here,
Daniel.
which is, these are because your customers know that these suggestions are coming from experts. Do they know how expert they are? Do they have a perception there? Is there a point at which their own tastes they may overrule because they actually believe these are coming from judgments? And have you experimented at all with the way that you present the authority of those expert judgments?
You are correct that there is a credibility factor, right? And I know this from the notes the customers write us on my own wife trying the service. This is part of the value, is they have a credible expert that's telling them, here's what's going to look good on you. And people are susceptible to it, right? They want the advice, and so they do opt in for this, and it's a believable thing. And so there's a question if how do you know if it's just the bias or is it actually right? So we won't know.
Last question, please. Stand in the front.
Yeah, I have a question that's, I think, related to the previous two questions. I was a bit surprised to see that there's even data at the bottom left, right? So meaning, like, why would you actually collect labels on stuff where you think it's very unlikely that they're going to purchase it? But then to your point, you only get labels for the items you actually send. So how do you think about exploration, or how do you think about even validating predictions that are low, right? At some point, you have to incur some cost to verify that, indeed, this probability was low.
Good question. That's kind of two. The first one is why do we even send these things out down here? We knew they were going to be bad. We predicted they were bad, and we did it. The answer is there's a lot of variation here that is explained by the customer herself. We have customers more difficult than others. You have a 6-foot-tall, edgy girl that has very expensive taste, and what's the amount of inventory we have that's compatible with those preferences, right? It's going to be small sometimes, right? And sometimes we won't do well, and we're predicting, we're not going to do well. This is the best we have, and we're at the left side of this range. The second part of the question is really near and dear to my heart, is how do we preserve variation? We got agents here at work, algorithms, stylists, and buyers. All of them are risk averse, and they keep finding out what works, and they keep this darn winning and pruning that's happening, and we got to preserve variation. It's our means for learning. So we are injecting purposely into the system at various points some random stuff just to make sure we keep learning.
Thank you.
Thank you.
Thanks for the fascinating talk. Next up, we have Margie Novotny from Microsoft, who's going to talk about the process of generating recommendations as a collaboration between the user and the system. Thanks.
Whoops. Works so easily last time. Maybe that's it. Yeah. Oh. Oops. Now we have them swapped. Let's see, I'd rather. Oopsie. I think it's the, oh, I think it's actually, you have to have it plugged in. Sorry about that. Let's see here. Okay, let's just mirror it over. Okay, sorry about that. Yay. I'm very happy to be here. Thanks for inviting me. I have to warn you kind of up front that I don't have any of this sort of thing in my presentation. I'm a designer, not a data scientist, but I've come to a really deep appreciation of data science and machine learning through the work that I've been doing for the last few years. Specifically, I've been running a team that has been designing and deploying these very immersive prototypes where we allow, we're learning about how what aspects of the recommendation system is really fall on the creepy side of things and which aspects fall on the magical side of things. So everything I'm going to be talking about here is really from the user experience point of view. So some things we've learned, high-level things we've learned. I'm going to just dive in and talk about these things one by one. So let's say that you've solved the cold start problem and you have a bunch of killer algorithms and you have amazing content to recommend. You still can't deliver personalized recommendations on day one. And by can't, I mean really you shouldn't. And why is that? It's because personalized recommendations require personal information, and that makes people uncomfortable. People don't want to give personal information on day one necessarily. So you can think of, rather than thinking about the cold start problem as we have and many people in this room do, we've come to think about the problem as what I call the cold ramp. So what you see here is really this relationship, basically, between the personal information that people are willing to share and the personalized value that they get in return for sharing it. So what you ideally want, or what you ideally have on day one, is the user sharing as little personal information as possible, and then over time, as value gets delivered, people are more willing, they're actually interested in sharing more personal information as they see the value that's being delivered. So how would you model this? What does that diagram that I just showed you mean? I'll give you an example. So imagine that you find yourself at some event and you find yourself standing next to somebody and you start chit-chatting, and what you're going to do is you're not going to dive right into the personal stuff. You're going to you're going to talk about the Giants game last week. You're going to, talk about the bridge closure or something that's common to both of you. You might start chatting about the event itself that you're in. You're going to start in summary. You're going to start with something that's kind of general and common to both of you. So one of you might, say, wow, it's been super hot this last week, right? And if the conversation so far has been pleasant, one or the other of you is going to offer some nugget, some more personal nugget. So, one of you says, oh yeah, wow, it's been really hot last week, but it's supposed to be better weather this weekend, a little bit cooler, and better for mountain biking, let's say. So the minute somebody's offered, that nugget, it's an invitation for you to dive in about that subject. So now you can dive in and ask, oh, well, what kind of bike do you ride? And how often do you ride? And who do you ride with? And the person will offer things like, they'll tell you about their bike, they'll tell you about the riding group that they belong to, they might tell you about the vacation they took to Nepal last year with their wife, where they spent a month and a half biking around. What's interesting about this is you're well within the constraints of social protocol in this kind of exchange. The person has given you the clues that allow you to dive in deeper, and by diving in deeper, the answers that they give suggest a lot of different things. So, for example, the bike that they describe, it says something about their disposable income, or their frequency of riding, or the intensity of riding might say something about their household situation. And they mentioned doing a trip with their wife last year. So, okay, so they're married, right? And chances are they don't take off for 6 weeks to ride in another country if they have children, right? So there's all kinds of secondary information you can start to begin to guess by engaging in a very polite conversation. And this is just how our human brains work. So what we learned by building these prototypes and having people experience the actual experience of getting recommendations pushed to them directly, we learned that they only accepted them, or they only delighted by them if they respected social protocols, like I just described. So what we're talking about here is really trust. You can't deliver recommendations, or I'm speaking from the point of view of the user here. You can, but what the user actually wants is to understand, build trust with the system before they reveal a lot of personal information. So the way we've learned about building trust is really to have the system have some very explicit and overt way of learning. So learning should be a key feature of the system. And it should also be really transparent about what it's learned. It should be trying to expose the stuff, whatever it's learned, in the most immediate and accessible way for the user. And then it also needs to, it shouldn't be learning stuff that it can't deliver value on. So once it's learned something and once it surfaces to the user what it's learned, it better take advantage of that to connect what it's learned with content that the user is going to find valuable, because if it doesn't, if it's collecting information that it doesn't leverage, and if it's not able to deliver content that's relevant, people are going to lose interest and drop away. And of course, the last piece is asking for feedback. So the system really doesn't know. The system has to learn what kinds of things are really meaningful to the user. And the only way to do that is by making sure you have a closed loop system. And of course, when you get the feedback back, it's got to be an additional input into the learning cycle. So this is what we think of as the virtuous cycle in recommending. I've been working on a product that kind of embodies a bunch of this thinking. It's sort of baked into the foundation of a product called Cortana, which is something like some kind of a hybrid, sort of capabilities like Siri and like Google Now. So like Siri, Cortana has natural language capabilities. You can ask her to do searches. You can ask her to set reminders. You can chit-chat with her. But unlike Siri, Cortana remembers your sessions, and she's actively trying to build a picture of you based on what you do and what you say. So there's a visible profile that's being built. And like Google Now, Cortana is always trying to surface the content that she thinks you're going to need at any given time. So often it's triggered by context or by location, or it's in some other way. It's coming to you without you asking, ideally. And what makes that magical is that connection between making sure that it's using the information that is relevant and connecting it with content that we're certain you want and need. And the way this is different than Google Now is the transparency piece. So the transparency is super, super important in Cortana. Cortana can know or learn that I'm a parent. But I may want that learning to be applied in one thing she does for me and not in another thing she does. So for example, I might want her to use the fact that I'm a parent when she recommends restaurants to me. But I might not want her to use it when I'm trying to figure out an event for date night, right? So I have this capability of, I'm a parent, that's true about me, but I have the ability to determine how that piece of information, how and where that piece of information is used. Like Eric, who spoke before me, I think that there is a huge human component to this machine learning problem. I think we have to think about the psychology and the human values. We have to bake that into the recommendation process. And that's what we're trying to do with this new product. Thanks.
Hello. So at the risk of getting angry with some of my HCI colleagues in the room, I'm going to challenge some of the things you said or some of the approaches, because I'm assuming that you're drawing these very general lessons learned, like the one that you were saying. By the way, this is a way to start our panel that we're going to have afterwards on controversial issues, because I think this is one of them. You're claiming things like, for example, don't personalize on day one. And my question to that is, have you had any A/B test where you have a large population responding to this in a positive way, or are you basing this on asking a couple of people, how do you feel about your personalization on day one? And the reason I'm asking is because people, when you ask them directly that question, will respond a different thing than if you actually introduce it in a product and you give them the ability to interact or not. And there's been a large body on studies on cold start, as you know, that have shown positive results, right?
Okay, so the kind of studies that we did were not asking people questions. So we built prototypes of the product we envisioned, or aspects of the product we envisioned, and we had people use them for a week or 2 weeks, and in some cases a month. So I think in total we had maybe 225 or 250 people that we were experiencing the product, before it was a product, immersively. So the feedback that we got was really coming out of culling all of, we had direct feedback in terms of free feedback according to, associated with each recommendation we gave, and we had ratings associated with each recommendation we gave. And we also had, entry interviews and exit interviews. So from all this research, these were themes that came out. And so I agree with you. It's not, and we did try A/B testing where you had zero information about the user in some cases, and in other cases where we had a little bit or some key, we found like there are 8 or 9 key things that are really super vital to know about a user. So we've tried doing it both ways. So I'm not against cold start. I think what we learned was that in order for people to accept and be happy with a system like this, you kind of have to observe the social protocols that human-to-human relationships go through. You have to start with a more general sort of recommendation, and you have to progress over time and in context to more and more personalized stuff over time. That's what makes people happy. Otherwise, they get freaked out. And
sorry, you said for a system like this, you're not generalizing. You're saying it's for a system like this, or you think it's more general?
I haven't thought about where it wouldn't apply, but in general, I think that what I'm talking about is human psychology, and so a system like this, where it's presenting itself as humanoid, or it's clearly an embodied offering, right? So in this case, it's especially true that anything that's embodied wants to be polite and wants to observe the rules of social etiquette. It's risky for it not to.
Yeah, so you talk about keeping a model of the user and being able to sort of let the user see what their model is.
Mm-hmm.
And it seems to me like this is kind of similar to explanation in that you can surface that information at more or less detail and be more or less confusing in what you surface. And I was wondering if you had any comments about how you surface that information appropriately to people and what are kind of the trade-offs in that area.
Yeah, so we're really trying to surface information in a way that makes it, isn't so dense that people they get bogged down by it, but also it's hard to explain, but more, it's like we try to package inferences that we have about the user. So if you've learned that I'm a parent, it's not so maybe helpful to learn that I'm just a parent. What's really helpful is to know whether I'm a toddler mom, or whether I'm a teenage mom, or whether I'm an empty nester, right? So the profiles and the settings views of these systems tend to be very data-centric, and the model we're using is really, if I'm a parent or I'm a toddler mom, give that back to the user in those terms. Package it in a way that makes it intriguing to look at, so that you can look at your identity and be, kind of interested at what the system believes is true about you. And you might even, in theory, be interested in, you might be motivated to share your identity with somebody else on the system, because it's not presented in terms of legalese and radio buttons and settings. It's packaged in a way that it's like answering a Cosmo quiz or something. You're interested in the result. So we're striving for that kind of profile to emerge.
One last question. Anyone? All right. Thank you very much.
Thank you.
So that concludes the second part of the industry session. Please enjoy lunch, and we hope to see you tomorrow either at Facebook or LinkedIn. The buses leave at 10 a.m. tomorrow.